Greetings, fellow aliens. Welcome to my video about the nature of time. This is not an Earthlings 101 episode, but more oriented towards physics and philosophy. If you want to know what defines the direction of time, what it has to do with the Big Bang, why we remember the past and not the future, and whether time might be a macroscopic phenomenon, you're at the right place. The main subject of the video will be the different arrows of time and how they relate to each other, the thermodynamic arrow, the cosmological arrow, the arrow of radiation, the Fork Asymmetry, and the Record Asymmetry. An Earthling called Augustine once wrote, "What is time? If nobody asks me, I know, but if I wanted to explain it to one who asks me, I've no idea." In this video, I will try to answer that question. So, what is time? I probably don't need to explain spacetime to you, or the conglomerate as we aliens call it. One could define time as one axis of spacetime. But the problem is that people move around, tracing a path through spacetime, and the time axis changes when you move around. How does time pass for a traveler moving very fast, relative to us? For a long time, Earthlings believed that time was independent from space. This would mean that an object in spacetime behaves like a sliced sausage, every moment is a slice, and moving around is equivalent to shifting or shearing the slices. Imagine that one slice corresponds to one lunar cycle. In this model, somebody traveling away and coming back would have the same age as their clone who stayed at home. In other words, Earthlings used to believe time was absolute. My species doesn't separate space and time as much as Earthlings do. On my planet, people used to believe that the faster you move sidewards in space, the slower you move forward in time. This would mean that changing the reference frame is equivalent to rotating. In this model, time would be relative, as the traveler would be older than his clone when he returns. Turns out we were both wrong. Time is relative, but not as we Betelgeusians thought. Special relativity teaches that changing the reference frame is neither shearing nor rotating, but an odd hyperbolic turn-stretch movement. This means that the traveler will actually be younger than his stay-at-home clone. This stretch movement is called Lorentz transformation. The important point is that said transformation stays inside a double cone, defined by the speed of light in a vacuum. Nothing can go faster than that. In consequence, anything outside of these cones can't directly influence or be influenced by the present point in any way. So, you could define time not as an axis but as a double cone at every point in spacetime. One of those cones is called past, and the other one is called future. But which one is which? What's the difference between past and future? That's where things become interesting, and that's what this video is all about. In the central containment facility at Gaia BH1, we find anomalies number 7113A and B, a pair of strange monoliths that travel backwards in time. They are covered in a mysterious script from a future civilization, counting tales of events that haven't happened yet, and thoughts that are yet to be thought. They appear to be normal, unless you try to chisel away some of the material, then new letters appear out of nothing, adding text that was lost in the past. They're in containment because strange things can happen to your body when you touch them. More on that later. So, what defines the direction of time? You might be tempted to say that the direction of time is included in just about every law of physics, from falling objects to colliding particles. But you would be wrong. The strange thing is that the laws of physics are reversible. When you play the movement of planets backwards, they follow the same rules. The same can be applied to light, running through a system of prisms and mirrors, or an electric current moving a motor, or perfectly elastic 3D billiard balls colliding, or basically any other physical process, as long as you don't produce heat, break stuff, or make a mess. I will come back to those exceptions. The aliens among my viewers might have heard of the Blobox toys. In the outer parts of the galaxy, in a starless bubble somewhere between the Perseus arm and the outer arm, lies the Blobox system. Two black holes orbiting each other, with no planets, asteroids or gas, not even accreditation disks, and for some unknown reason no Hawking radiation. In one of the Lagrange points of the black holes, we find a saucer load of oddly shaped, perfectly elastic pink artifacts, bouncing into each other again and again, presumably since time immemorial. Who left them there and why is not known, and given the shape of the objects, it might be better not to know. My point is that those artifacts behave in a perfectly time-symmetric way. If you watched a hollow film tracking their movements, you wouldn't be able to tell if the film was played forward or backwards, because most physical laws work both ways. So, when the fundamental laws of physics are time-symmetric, why does time have a direction? Why do asteroid craters not spontaneously eject asteroids? Why can't you unstir a pangalactic gargle blaster? And why do we get older and not younger? The goal of this video is to identify asymmetries in time, physical laws that work only in one direction. We might call those laws arrows of time. An arrow is an archaic earthling projectile weapon that makes it very clear on which side you want to be, and it's widely used as a symbol for direction, like the warp wake on hyperspace traffic signs, or the waiting line in administrative signaling. The first and most famous arrow of time is the thermodynamic arrow, better known as entropy. Remember what I said before, the laws of physics are mostly reversible as long as you don't produce heat, break stuff or make a mess. In other words, when you transform order into disorder, there's no going back, unless you pump more order into it to clean up the mess you made. That's the second law of thermodynamics, which roughly says that disorder increases with time. But how do you define disorder? Imagine a variant of the Earthling's game of chess where we have 16 knights on each side, the pieces move around randomly, and you can't take other pieces. The initial state is very orderly, and there is only one possibility of placing the pieces, assuming pieces of the same color are indistinguishable. One could say that this state is very unlikely to occur by coincidence. There are more possibilities or microstates to place all pieces in their first 3 rows, and even more microstates to place them in the first 4 rows. As for the number of microstates to place them all over the board, there are about 100 septillion possibilities, if I'm not mistaken. Of course, every one of those microstates is just as unlikely as the first one. Now imagine that we're watching the board from orbit with a bad camera, so all those messy possibilities are lumped together into the same blurry gray image. We call this a macrostate. That all-gray macrostate corresponds to gazillions of microstates. When the blurry image shows a clear separation of black and white, we have fewer possibilities. And when it shows that all pieces are in their start position, we have only one possible microstate. So, seen from afar, the less orderly a macrostate is, the more microstates it combines, and the less we know about what the actual microstate is. You might have guessed it, my chess pieces represent particles, the fields correspond to the states of the particles, and the blurred vision from orbit is our macroscopic view of the world. And the number of microstates hidden in a macrostate, that's basically what Earthlings call entropy. Consider an Earthling dessert, the affogato, which consists of cold ice cream and hot coffee. In its initial state, the number of microstates is rather high, but still constrained by the fact that all coffee molecules are in one place, all ice cream molecules in another place, and the ice molecules don't move very much. Once it's all molten and mixed up, the number of microstates is way higher. In other words, the second state has a higher entropy. Now, the second law of thermodynamics says that in a closed system, entropy increases with time. That means that an affogato tends to transform into a lukewarm coffee vanilla cream, but never the other way around. By the way, when you look at the definition of entropy, you'll find that it's not exactly defined as the number of microstates per macrostate, it's the logarithm of that number. The reason is rather funny. As you know, Earthlings are obsessed with things, and they like quantities that add up like things. Most of their made-up values do. The mass of 2 systems is the sum of both masses. The same holds for energy, volume, momentum, angular momentum, or electric charge. Heck, even their totally made-up monetary value works this way. But if they define entropy as the number of microstates, they run into a problem. When you combine 2 systems, the numbers of states don't add up, they multiply. Earthlings didn't like this, so they placed a logarithm symbol in front of that number, because a logarithm turns multiplication into addition. With this little trick, entropy adds up like objects, and they can imagine it as a thing, an invisible stuff that floats around like smoke and is impossible to get rid of. The mist of chaos, if you will. That's Earthlings for you. The important thing to remember is that low entropy means order, concentrated energy, and neatly separated mass, an unlikely state. High entropy, on the other hand, means disorder, diffuse heat, and mixed up mass, a likely state. Now, the thermodynamic arrow of time is the transition from low to high entropy, from unlikely to likely macrostates. That's the second law of thermodynamics, and it seems to be the main reason why time has a direction. For example, the other laws of physics don't explicitly forbid that the heat inside a fresh asteroid crater creates a spontaneous movement of asteroid fragments which assemble like a puzzle, and eject the asteroid into space. But this doesn't happen, because it would increase order and decrease entropy. Of course, you could build an orbital mirror array to create a heat ray, provoke a volcanic eruption and catapult molten rock into space, but that would require pumping low entropy in the form of sunlight into it. The world as we know it is literally powered by low entropy. Many young planetary civilizations receive most of their energy from their local star, directly or indirectly. But energy, in this context, means low entropy, because once that energy has been transformed into uniformly distributed heat, it's still energy, but pretty much useless. That's why many pre-warp civilizations struggle with both energy shortage and planetary warming. Thermodynamics is why it is so dangerous to approach anomalies number 7113A and B. Entropy doesn't behave as it should in the vicinity of the monoliths, especially when you touch them. Reports speak of spontaneously healed fractures and reversed aging, but also of frozen limbs or boiling intestines. One unlucky researcher had even their bones laid out on the floor in alphabetical order. That's because when time runs backwards, entropy decreases and order increases. It is important to note that the whole concept of entropy is statistical in nature and relies on our blurred vision of the world. If we watched a film of individual particles inside a melting affogato, we wouldn't be able to tell whether it's played forward or backwards. The direction of time, as defined by thermodynamics, seems to be a macroscopic phenomenon. We will come back to that towards the end of the video. Can the second law of thermodynamics somehow be deduced from the other laws of physics? Given that the other laws are symmetric in time, the answer is no. In any argumentation, laws of physics, something, arrow of time, there must be some asymmetric assumption hidden in one of the something steps, otherwise, you could apply the same argumentation to the time-reversed case and get the opposite result. This is called Loschmidt's paradox. Let's get back to our chessboard. Even if the random movements of each piece are reversible, the entropy of the whole board rises with each random movement of the pieces, they move from unlikely to likely states. Some believe that the direction of time simply comes from the fact that the pieces just so happen to have been put in a low entropy state at the beginning of the game. This is called a border condition. Maybe, so the speculation goes, if the low entropy state had been at the other end of the game instead, time would flow in the opposite direction. This leads us to the next arrow of time, the cosmological arrow. So, where do these border conditions come from? As mentioned before, the low entropy usually comes from a star. The star gets its low entropy from its reserves of hydrogen and helium atoms, which were created at recombination, after the Big Bang. All low entropy sources can be traced back to the ultimate source of low entropy, the Big Bang. But Zarg, you might object, wasn't the Big Bang extremely messy and disorderly, way messier than a molten affogato? How can that be low entropy? Sure, it was messy, but it was concentrated in way less space than we have now. An expanding universe is like an expanding chessboard. The further we go back in time, the smaller the board, the fewer possibilities to place the pieces, and the lower the entropy. Imagine the whole universe concentrated to the volume of an affogato glass. That reduces the possibilities for the microstates, doesn't it? So, the whole universe is powered by low entropy, which ultimately goes back to an affogato-sized universe shortly after the Big Bang. Some think that this is the source of the direction of time, the Big Bang as the ultimate border condition. This is called the past hypothesis. Centauri cosmologists go one step further. They believe that the universe will one day reverse its expansion and end up in a big crunch. If time is powered by cosmological border conditions, this would imply that time will run backwards in the second halftime of the universe. Which would be, by the way, the first halftime for people who live there. Earthlings call this view the Gold Universe, named after the cosmologist Thomas Gold. Actually, Gold Universe doesn't mean it's a closed loop, that's a Centauri belief. Back to the Blobox toys. A while ago, a group of Centauri scientists tried to extrapolate the movement of the artifacts to see if there was a time when they were arranged in a regular pattern. They didn't find any such point in the past, but they claim to have found one in the distant future. A trillion standard cycles from now, those toys will be arranged in a perfectly packed pattern, just like one would store them in a cargo hold. The Centauri claim that this might be a hint that the artifacts come from the distant future, not unlike anomalies 7113A and B, retro relics from an era when the universe will contract and time will flow the other way. I find this hard to believe, but the idea is intriguing. Every alien civilization sees the universe differently. The Polari, for example, imagine the cosmos as a four-dimensional fabric, filled with high entropy but studded with low entropy dents. Earthlings would call them Big Bangs. Around each of those Big Bangs, we have gradients of increasing entropy pointing outwards, and those gradients define time. Because life as we know it relies on sources of low entropy, it can only thrive on those entropy slopes, like an Antarian sloped chicken. What Earthlings call dramatically the heat death of the universe, is in this model simply the lifeless and timeless deserts of maximum entropy that fill most of the universe. Anyway, let's consider another asymmetry in time: radiation. Look at those two animations of waves in a pond. Can you tell which one is playing forward and which one backwards? Of course you can, because you know that waves on a surface expand in concentric circles but don't contract in the same way. The same holds for waves in three-dimensional space, be they sound, radiation, or even gravity waves. This is called the arrow of radiation. Note that similarly to the thermodynamic arrow, this is a macroscopic asymmetry of time. On a particle level, absorbing a particle looks like emitting one backwards. But on a macroscopic level, we have lots and lots of radiation sources but no radiation sinks. You might think of black holes, but they don't behave like backwards emitters. Put a black hole into a big void, and you don't get a constant flow of radiation aimed at it out of nowhere, you only get a gravity well that catches the little radiation that happens to pass nearby anyway. Some alien scientists believe that such radiation sinks do exist, but that we are unable to detect them with conventional telescopes. The Aldebaranians are even constructing a sink telescope that won't detect incoming but outgoing radiation. It's not clear whether and how the arrow of radiation is a consequence of the second law of thermodynamics. But for both phenomena, we have an abundance of sources of low entropy and of radiation, and a total lack of sinks. Those sources date back to the Big Bang, and maybe the lack of sinks comes from the fact that there is no big crunch in the foreseeable future. Maybe, if we live in a gold universe, things will be the other way around in the second half-time. Who is to know? When you look at the continents of Earth, you will notice that the western coastline of Africa and the eastern coastline of South America are strangely similar, too similar to be a coincidence. Is this because the continents are preparing to collide in the future? Of course not, it's because they go back to a supercontinent that broke apart a long time ago. So we have two correlated states in the present, which are linked to a third thing, and we know that this third thing must lie in the past, not the future. Earthlings call this a common cause. That's called Fork Asymmetry. When two or more events or states are correlated, this correlation goes back to a common cause, and this cause lies always in the past, never in the future. This asymmetry seems to be due to the thermodynamic arrow of time. Our continents with matching coasts are not much different to a broken egg, and the former supercontinent had a lower entropy, just as the whole egg had. Whenever you find a fork asymmetry, you also find a situation where entropy has increased. If correlations occur after entropy increasing events like breaking an egg, does that mean that correlations contribute to the entropy? I think the contrary is the case. Before the egg is broken, the parts are even more correlated as they stay close together, which greatly reduces the number of possible microstates. Once the egg is broken, we have correlated nearby fragments. The more the fragments break apart, the less they are correlated, until eventually, all perceivable correlation is lost. Fewer correlations allow more microstates, which means higher entropy. In other words, correlations over a distance are the remnants of fading order, the keepsakes of past encounters, a side effect of the transition between low and high entropy. It's like when you rip a grilled cheese sandwich apart. That fact that it's broken is the increased entropy. The molten cheese represents the correlations, and the strings of cheese between the parts indicate that the sandwich was ripped apart not long ago. You can see it like this: suppose we see two triangular sandwiches that seem correlated over some distance. Relativity teaches us that each part can only influence or be influenced by things in their respective light cones. That's the principle of locality. So, both parts must be correlated to a common sandwich, some interaction in the intersection of the light cones. But during that interaction, the parts are even more correlated. We can conclude that the common sandwich must lie in the past, not the future, because it has less entropy than the ripped-apart sandwich, and entropy always increases according to the second law of thermodynamics. Hence, thermodynamics can explain the fork asymmetry. I think the fork asymmetry can in turn be used to explain the asymmetry of radiation. Because what is a wavefront other than a very roundish fork, pointing back to some common point in the past? But I might be wrong about this. The arguably most obvious distinction between the past and the future is that we can remember the past but not the future. More generally, we can have records of the past, but not the future. But why? Take, for example, this picture of an alien saucer taken in 1950 in Oregon. One single pixel of this picture wouldn't mean anything, but taken together, they are correlated, forming the distinctive silhouette of a vintage Turbospin 3000 family saucer. Now, remember the fork asymmetry. What did we learn about correlated states or events? They must be linked to some past event, in this case, to a careless alien tourist family decloaking 75 years ago over the American countryside. The key is that records are always highly correlated data points, aka patterns, pixels on a photograph, symbols in a cornfield, encoded sound waves, written text, patterns of neurons wired together, whatever. In other words, a record is a fork with many correlated tips, always rooted in the past, never in the future. But can't a record consist of one single bit of information? Hardly, because it needs context. When you find a sticky note with the word no on your piloting console, that doesn't mean anything, unless it comes with a memory giving it meaning. Maybe it indicates whether or not you did clean your hyperjump manifold before taking off. The same can be achieved with a text, or a picture of the clogged manifold, or a warning light with a label. A record always needs to contain enough correlated information to get the context, and to reconstruct the fork rooted in the past. That's why you can remember the past but not the future. This is called the record asymmetry, or the psychological arrow of time. I've also seen attempts to explain the record asymmetry directly with the second law of thermodynamics. Apparently, both memorizing and forgetting require energy, and increase entropy. But I find the explanation with the fork asymmetry easier to understand. Let's resume the asymmetries we have identified so far. First, we have the thermodynamic arrow, aka the second law of thermodynamics. Then we have the cosmological arrow, which may or may not explain the thermodynamic one. Then, we have the arrow of radiation and the fork asymmetry. And finally, there is the record asymmetry, aka the psychological arrow of time. If the thermodynamic arrow can explain the fork asymmetry, and the fork asymmetry explains both the asymmetry of radiation and the record asymmetry, we have linked everything to thermodynamics, and what appears as different arrows of time are really just manifestations of the second law of thermodynamics. However, we have seen that the second law of thermodynamics is a macroscopic phenomenon. It depends on the blurring when we zoom out to macrostates and disappears when we zoom in. So, is there a direction of time in microphysics, anyway? We will come back to this question towards the end of the video. Earthlings will tell you that there is another arrow of time, causality. My alien viewers have probably no idea what I'm talking about, so let me briefly introduce the concept. When two successive events are directly linked, Earthlings call the earlier one cause and the later one effect. The effect can then cause other events, which cause other events, and so on. For us aliens it's only two words, but for Earthlings, it's apparently a big deal, one of the premises of how they perceive the world. They see the whole universe as a big tree of chains of causes and effects, with causes conditioning the effects like branches supporting twigs. For Earthlings, all of history can be explained with cause and effect. To give an example, when object A collides with object B, which then collides with object C, the first collision is called the cause, and the second one is called the effect. Earthlings perceive the direction from cause to effect as a very obvious arrow of time. My alien viewers will object that this is nonsense, and rightfully so. When you play the chain of events backwards, the same laws of physics apply, and cause and effect trade places. In consequence, the distinction between cause and effect doesn't give time its direction, but the direction of time is used to define what's the cause and what's the effect. But try to tell that to Earthlings. Of course, not every chain of cause and effect is reversible. A second collision might break the object. But that's not a new arrow of time, it's just our old friend, the thermodynamic arrow. Some Earthlings have tried to take time out of the definition of cause and effect. That's called interventionalist causality. It goes like this. Assume we have an event with a cause and an effect. When you interfere with the event, that changes its effect but doesn't affect its cause. But this doesn't change much, because the very notion of interference is linked to the direction of time. When you play the events backwards, the interference becomes a side effect. So, Earthlings basically insert another temporal asymmetry to obtain their beloved cause and effect asymmetry. That's the Low-Schmidt paradox all over again. You can't get asymmetry out of symmetry. So, I think we can dismiss the supposed arrow of causality as temporally biased Earthling psychology, rather than physics. Before we delve into time in microphysics, a word from our sponsor, the Schwarzschild distilleries.
The center of the galaxy is not for the faint of heart. Surrounded by a vortex of gas clouds, inside a hollowed-out star cluster, lurks a star-devouring monster. Sagittarius A star, the mother of black holes, nicknamed Leviathan. Orbited by massive stars, with the mass of millions of suns, it is so majestic that time itself slows down in awe in its presence. It is here that we create the finest drink in the galaxy, Leviathan Dark. Collected in the ring of molecular clouds around the galactic core, aged in the fossilized skins of ancient Arcturian sand whales, and refined through the crushing tidal forces of the central black hole itself, Leviathan Dark is a Sagittarian brandy without equal. Leviathan Dark, the brandy from the edge of time.
Now, let's talk about microphysics. Most Earthlings don't seem to realize how much their concept of causality influences their thinking. It is one of the postulates Earthlings use instinctively when thinking about reality. Let's try to list some of those postulates. Unity, there is only one universe. Ontology, the universe consists of things. Reality, each thing is in one specific state at any given moment. Causality, states are only determined by the past. Locality, things are only influenced by their immediate surroundings. Free will, choices are not predetermined. Now, when dealing with microphysics, Earthlings realized that they had to drop at least one of their beloved postulates. However, they are very reluctant to drop causality. Most of them would rather split the universe into many, speculate about spooky action over distance, doubt the existence of things, or drop the concept of states altogether than admit that states might sometimes depend a little bit on the future. The reason seems to be that in order to admit that, one might have to give up another concept Earthlings are very fond of, free will. The idea that particle physics is time-symmetric is not so far-fetched. Consider, for example, an electron absorbing a photon. We can draw this as what is called a Feynman diagram. The time axis goes upwards, arrows indicate electrons, waves indicate photons. Now, this is a photon absorbed by an electron, but if we turn the diagram to the left, we get an electron emitting a photon. Turn it again, and we have one arrow pointing backwards in time, which we interpret as a positron. So, this diagram shows an electron and a positron annihilating each other. If we turn again, we get a positron emitting a photon, then a positron absorbing a photon, and eventually a photon transforming into an electron-positron pair. The point is, if we interpret a positron as an electron going backwards in time, we discover that 6 different kinds of events are basically the same thing, if we ignore the direction of time. So, maybe microphysics doesn't really care which way time goes. Maybe time is in the eye of the beholder. To play with this idea, let's make a little thought experiment. If you're an Earthling, think of it as science fiction. Imagine your favorite made-up space heroes stumble upon a planet where, on a quantum scale, the laws of physics are time-symmetric. What do I mean by that? Consider 2 physical entities that interact with each other, resulting in a third entity. In the ordinary world, when we maintain one incoming leg and change the other one, this changes the outgoing leg. But in our fictional world, if we fix one leg and change a second one, this changes the third, unobserved one, even if that's one of the incoming legs. Think of it not so much as causality but as a crossword puzzle. When we know one word and write the second one, this determines the third, unknown one, no matter in which direction it points. This would be a strange world, unlike anything we know. In this world, an electron aimed at a double slit would behave like a wave or a particle, depending on how it is measured. If it's not disturbed before it reaches the slits, it behaves like a wave, passes 2 slits at once and creates a nice interference pattern. But if it's observed, it behaves like a particle and passes only 1 slit. It's almost as if it had been a particle all along, due to the observation somehow crossword puzzling back in time. Sounds crazy, right? In this purely hypothetical world, we might have pairs of entangled particles with opposite states, but those states would somehow depend on how we measure them. Measuring one particle would fill in the crossword puzzle, it would somehow propagate back in time for one particle and then forward for the other one. A strange world, indeed. What would happen if Earthlings, with their causal thinking, would visit this peculiar world? They would see that particles behave differently when observed and conclude that they are in some kind of superposition of multiple states, until observed. They would see the connection between entangled particles and interpret it as a spooky action at a distance. Yet, Earthlings aren't stupid. They would probably create a consistent mathematical model around these observations, one that delivers accurate predictions. However, they would struggle to make sense of this model because it would conflict with their precious postulates. Some Earthlings might point out the absurdity of superposition and spooky action, suspecting some hidden variables at work. Others would prove that hidden variables aren't possible, but only for hidden variables that are independent of the measurements. In other words, their proof would rely on forward causality thinking. They would defend that causal thinking with rational arguments like the grandfather paradox, and less rational ones like their ardent desire to maintain their beloved concept of free will. Some might even get emotional and start kicking and screaming at anyone who dares to question the idea of free will. The ensuing debate would be one which, like most macroscopic processes, creates more heat than light. In other words, that world would be strikingly similar to our own, a world with strange quantum phenomena, incomprehensible to earthlings who think causally, and with heated discussions about which postulates must be dropped to maintain the ones they're emotionally most attached to, the holy cows of causality and free will. I'm anything but an expert in quantum physics, and I'm not claiming that a time-symmetric approach solves or fixes quantum physics. No matter the interpretation, quantum mechanics seems to be a great tool to describe reality, or maybe to describe what we can know about reality at any given moment. All I'm trying to say is that maybe, just maybe, when considering which postulate to drop to explain quantum mechanics, the idea of dropping the temporal asymmetry of causality rather than other postulates might merit more attention. And, earthlings, if you are so adamant about maintaining your beloved free will, just consider it a macro phenomenon, like the thermodynamic arrow of time, which may sometimes retro-propagate back to the past on a microscopic scale. Nobody is out to take away your agency and transform you into a marionette. Except for the brain suckers, of course, but that's another story. To be fair, there have been attempts by earthling quantum physicists to make quantum mechanics time-symmetric, the Wheeler-Feynman absorber theory and the transactional interpretation, superdeterminism, retrocausality. But I don't know enough about microphysics to comment on those. If you want to learn more about superdeterminism and the controversy around free will, I recommend the videos by Sabine Horsenfelder. Link in the doobly-doo. I think superdeterminism is pretty close to my metaphor of the universe as a crossword puzzle. Or maybe a Sudoku game. As Emily Adlam once said, God doesn't play dice, he plays Sudoku. This video, and especially the last part, is mainly based on the book Time's Arrow and Archimedes' Point by Hugh Price. Price isn't a physicist, but a philosopher, not the kind that jabbers about the thing by itself or the nothing which nothings in the nothingness of nothingitude, but a philosopher of physics who seems to know more about physics than many physicists. In my opinion, this book's main merits are pointing out temporal double standards in discussions about time, as well as proposing the mechanism I illustrated with a crossword puzzle. Price calls this advanced action. Hugh Price was so kind to skim through this script to check if there were any blatant errors. Thank you. We have seen that the arrow of time is mainly a macroscopic phenomenon, possibly driven by the temporal asymmetry of the universe. Whether or not time has a direction in microphysics remains open, and may depend on observations yet to be made. See what I did there? Anyway, this was my video about the nature of time. If you have comments or detected some errors, feel free to comment. If you don't, comment anyway. My next video will be about something completely different, an ancient earthling concept to explain reality, arguably older than causality, the concept of magic. So long, like, subscribe, and don't forget to be alien.